Hey there, in this video we are going to look at what a logarithm is, what the log key on your calculator does, and how you can determine and estimate what are called common or base 10 logarithms. Now we're going to start by using a calculator to investigate what a logarithm is by using the logarithm key. Any scientific calculator is going to have a logarithm key on it. On this calculator it's right here. So we're going to start by just trying some random numbers here. Let's say we're going to do logarithm of 300, let's try. And maybe logarithm of 81. And logarithm of, I don't know, 47,521. Let's see that. We've got three values there so far. Seems like numbers, these decimal numbers here. Let's try one more. Let's try one smaller than 1. Logarithm of, I don't know, 0.00652. And see what we get there. So you might not recognize what those are. Seems like if you're looking for some patterns, the bigger the number is, the bigger the logarithm is. This number is the smallest by far, and it actually has a negative logarithm. Now, I'm going to steer you a little bit in the right direction here. We're going to try some very specific numbers here. We're going to try some powers of 10. So say logarithm of 1,000, and you get 3, and logarithm of 100, and you get 2. If we keep going here, logarithm of 10, you get 1. You might be able to start predicting what's happening here. Now, you might not think of 1 as a power of 10, but it is. Logarithm of 1 is 0. If I keep going here, I'm going to do some smaller than 1, like I did before, but I'm going to put 0.1, 1/10. Its logarithm is -1. Well, if I keep going, 0.1, log of 0.001, and you get the idea here. We could skip a few here and go logarithm of 0.0000001. We get -7. And let's try a big number here too. Logarithm of, let's say, 1,000,000. How about that? Now, those are all powers of 10, and you notice that the logarithm is an integer, not a decimal. Like the random numbers we tried first, we got these decimal numbers, but these are all integers. Now, before we go back and more fully analyze this, we're going to look at some numbers that are somewhere in between the random numbers I tried first and these powers of 10 here. So we're going to do something like this. Let's say we're going to try log of 5,000. We're going to try log of 500, like related to that number. If I keep going here, log of 50, and you notice something's happening there. Now, they're not the whole number of integers that we got before, but there is sort of a pattern you can notice that that's going down by 1 every time. If I continue this, log of 5, log of 0.5, then we have log of 0.05, log of 0.005, and so on. So let's organize this into some tables and see what we're dealing with. Now here's all the values that we found on the calculator organized into 3 different tables there. We have our numbers that were just sort of random numbers we put in first, and then those powers of 10, and then these other numbers which aren't powers of 10 but aren't completely random either. And looking at some patterns there. So we're going to start with this table here because that's probably the most obvious one where the pattern is evident, and you might have already started to get a sense of what a logarithm is here, what the logarithm key does. So all of these numbers are powers of 10. So for example, when you push the logarithm key, when you find the logarithm of 1,000, it tells you 3. And when you find the logarithm of 100, it tells you 2, and so on. That is because what it's telling you is this is what power of 10 it is. The logarithm key tells you what power of 10 a value is. So even these other decimal ones here, this is like 1/100, or 10 to the -2, so its logarithm is -2. All right? you can think of it as how many times you've multiplied by 10 here, right? So when you have 1,000, it's like you've multiplied by 10 3 times, 10 to the third 3 times, right? When you have a 1, you haven't multiplied by 10 at all. It's a 0. When you've, the one I looked at before, that one, 1 over 100, you haven't multiplied by 10. In fact, you've divided by 10 a couple times, which is why that's a negative, right? Now, can we make sense of some of these other ones here? If this is what power of 10 it is, what do these numbers represent? Does the same thing hold true here? Well, let's take this one, for example, here. The log of 81 is that. So if what we're saying here, and we're speculating, is that the logarithm of a number is what power of 10 it is, then I should be able to go to my calculator and go 10 to the power of this number and get 81, which we will do right now. Okay, so we just said log of 81 was that number. So now if I do 10 to the power of that number, which I'll do right now, if I put this in here, 19084855019, I'm going to get that number, which is very close to that. And the reason is because even though this is all the calculator shows, there are actually more digits that this keeps going. This is actually an irrational number. It just keeps going on and on there, but this is all the calculator shows, so that's as good as it can get. In fact, if I wanted to save myself some time and see a more exact answer, if I had gone log of 81 and found what that is, and now if I did 10 to the power of that number, what I can use is this answer feature down here, and if I do that, it has more digits stored than it shows on the screen, so that becomes a far more accurate answer there. The same with some of the other ones. Like one of the other ones we had there was logarithm of 47,521 was this number, and then if I now check 10 to the power of that number, 4.67688557, again, this is going to probably only give me a very close number there, right? 0.99999. Or of course, if we had done that again, log of 47,521, and we could go 10 to the power of answer, so that we use all the accuracy the calculator has inside there, you get that much more accurate answer, 47,521. So this number in this column is the power of 10 that it is. In other words, it's the exponent that you need to raise 10 to get the number you started with, right? We just saw that this is the exponent. I needed to do 10 to the power of that to get this number, and so on. Now, when you look at either of these tables, you also notice some other patterns here, that every time I go up one step there, this is 10 times bigger every time I go here. Number that is 10 times bigger there, its logarithm is 1 more, right? Multiplying the number I'm starting with by 10 is the same as adding 1 to that logarithm. And it's true even over here for these numbers that are not powers of 10 and these decimal numbers, right? The logarithm of 5 is 0.6987. The logarithm of 50 is 1 more than that, and 500 is 1 more than that. Every time I multiply by 10, the logarithm is 1 more. All right, so maybe let's summarize some of this, what we've found here. The logarithm key on a calculator gives you what power of 10 the number is, or in other words, the exponent that you need to express that value as a power of 10. Now, something that we didn't try here is, do negative numbers have logarithms, or does 0 have a logarithm? Now, we're going to go back and have a look at that on the calculator. So if I do logarithm of 0, it tells me that there's an error there. And there's a domain error, which means the number I'm putting in here is not okay to put in for this function. This button can't calculate the logarithm of 0. And similarly, if I put in logarithm of some negative number like negative 87, Same thing here. It gives me an error because there's no logarithm of that value. So 0 or negatives don't work. Their logarithms are undefined. And the reason is because there's no exponent that you can use with a base of 10 to generate a negative number or 0. So in other words, if you say 10 to the power of something here, and I wanted to get that 0, there's nothing I can put in there that's going to give me 0. Or there's nothing I can put here to get a negative number like the one we had, negative 87. There's nothing that works there to give you that number. So these only work with positive numbers. Logarithms are only defined for positive numbers. Now, something else that's worth taking note of from the numbers that we found is which logarithms are negative in our table there. The logarithms, if you look back here, the ones that were negative, so there was one negative in our random numbers we started with. There were 4 negatives here in these powers of 10, and then there was 3 negative ones here. If you look at them, all of those numbers are less than 1. They're all lower than 1. You could try numbers up to 1 but less than 1, and you'd always get a negative number for an answer. And while we're at that, you notice that the one that is 0 is when you take the logarithm of 1. And we saw why that was before, because 10 to the power of 0 is 1. All right, so numbers that are less than 1 but still positive, we should probably put in brackets there. But positive, right? Because we just saw you can't have negative numbers in there. The last thing we should think about here is, if you notice in the pattern up here, we said we were adding or subtracting 1 here when you jump 1 in the table. When you have a number that is 10 times as much, going from there to there to there, or whatever, the logarithm goes up by 1. You're adding 1 to the logarithm. Now, if you're going down the table, the logarithms go down by 1. Now this is this divided by 10, this is this divided by 10, so you'd expect, now where did that set of digits go? Well, if you look at it, subtracting 1 from this number, 0.7 roughly, right? This is 0.7 roughly, gives you 0.3 roughly. So that still is 1 lower right there. And then as you keep going, it just keeps getting 1 lower, like that. All right, so that pattern is still there. Right, the pattern's actually still there. It decreases or increases by 1 when you go up and down the table. It's just that when you cross over 1, when you take the logarithm, that 0.301, etc. appears. All right, so let's summarize this idea. So a logarithm, now we're going to specify here though that it's base 10. The number system we're working in is base 10 because you'll see later you can have logarithms that are in other bases, but we're going to leave that for another video. Sometimes these are called common logarithms because they're based on our common number system, which is base 10. The logarithm of a number is the power of 10 that the number is equivalent to. Or in other words, it's the exponent that you require to express that number as a power of 10. Right? So one of the ones we saw there was logarithm of 1,000 was 3, and the reason is because 1,000 is 10 to the third power. Those are equivalent statements. This one uses a logarithm, this one uses an exponential expression. So down here, logarithm of 100, which is not actually 4, not sure why I have that there, but logarithm of 100 is 2 because 100 is 10 to the power of 2. Logarithm of 20, if you use a calculator, you'll find it's that number because 20 is 10 to the power of 1.3010. I'm going to put some dots there. And what we should do is change this to roughly equal to, as we saw, unless we have all of those digits are what the calculator found for us. Now, the two keys that we were using there, we were using this key, and I was putting in 10 to the power of. Those two keys on a calculator. This one happens to be called the log key for obvious reasons, or the logarithm key usually, but this one is often referred to as the anti-log key for base 10, or common logarithms. These functions, because of that, these functions are inverses of each other. In other words, they undo what each other did. As you could see what we were doing on the calculator before. You can try it yourself. For any number you choose a number, find the logarithm of that number, and then find the anti-log of the result. What are you going to find? You're going to find it's the number you started with, just like what we did before. Now let's just try a few things here to make sure we've nailed down the concept. So first of all, just determining some logarithms of powers of 10 without a calculator. Log 100, as we saw a minute ago, was 2, and the reason for that is just because 100 is 10 to the power of 2, and that exponent on 10 is what the logarithm is. This value here, this looks like, if I count my zeros, that looks like 10 to the power of 7, so this is going to be 7, right? Because that is 10 to the 7th. This is what you're thinking to determine this number. You're saying to yourself, what power of 10 is that value? So in this case, what power of 10 is this value? You can think about it like a fraction. That's actually 1/1000th, right? Because that decimal is 3 spots over. So you can think about it like this. You can think about it like this, 1 over 10 to the third, or you can think about it like this, 10 to the negative 3, and that's the one that's going to get you the value here because it is negative 3, because 0.01 is 10 to the negative 3. Log of 1 we saw before was 0, and the reason is because 1, to express it as a power of 10, you need a 0 there. That's the exponent that you need. Now these ones look a little bit uglier, I would say. This square root of 10 here. So square root of 10, what we're going to do is go back to what we were thinking up here, thinking whatever number we're trying to find the logarithm of, what power of 10 is it? So we're thinking, what power of 10 is this? So if we are thinking here, we're thinking, what power of 10 is that? Root 10 is what? How can you write that as a power of 10? And you can write that as a power of 10. Root 10 is the same as 10 to the power of 1/2. So logarithm of root 10 is 1/2, or if you wanted it as a decimal, 0.5. And the same thing here, we can use that same concept of roots. So we're thinking now of, well, this might be a little bit more thinking, so we might need a little bit of a bigger bubble here to do some thinking. We have 5th root of 1,000. So 5th root of 1,000 is like the 5th root of 10 to the 3rd power. And the 5th root is like that to the 1/5, an exponent law. So you have 10 to the 3 to the 1/5. 10 to the 3 to the 1/5, you can write that as, I'm out of room in my thought bubble there, so 10 to the 3/5. Multiply those two exponents there when you have a power of a power. So this is actually 3/5 because the 5th root of 1,000 is 10 to the 3/5, right? All right, let's try something else here. Now, here's some values that aren't nice powers of 10, and we would, of course, need a calculator to work this out. But first of all, we're going to try doing some estimating here because you can use your idea of what logarithms are to give a half-decent estimate of what these things are. I think it's going to help your understanding to try and do that, even though we're going to punch them into a calculator to find out after. So a logarithm of 85, we don't know what that is, but we can kind of pin it between two values that we know. We can think of one that's higher than it. So we're going to write this one in the middle here and think, okay, 85, if I go up from 85, the next nice number I can think about the logarithm of is 100. So logarithm of 100 is 2, right? Because 100 is 10 to the 2. And we know this has to be less than that because it's going to take a smaller exponent than 2 to get 85. But if we go down to the next lower power of 10, we have to go all the way to 10, log of 10. So we know that it's bigger than that. Log of 10 is 1, right? Because 10 is 10 to the power of 1. That's the exponent you need. So log 85 has to be between those two numbers. It's got to be bigger than 1, but less than 2. So in between 1 and 2. Now, you can think, well, 85 is kind of closer to 100 than it is to 10, and that might give you some idea. It doesn't work exactly like a kind of a linear scale, but you can make a half-decent estimate by realizing it's got to be 1 point something. And since it is quite a bit closer to 100, maybe we're going to say that it's 1.9 or something like that. 1.8, 1.9, you might guess. And if you check it on a calculator, you will find that it is approximately 1.9. That's what it is. All right. The second one here, logarithm of 1160, if we pin it in between two numbers like we just did, logarithm of 1160. If you go down to the next nice power of 10 below it, you're looking at 1,000. So you've got log of 1,000. It's got to be bigger than that. So it's got to be bigger than 3. Log of 1160 has to be bigger than 3. But if we go up to the next power of 10 above it, log of 10,000 we have to go to. Log of 10,000 is 4. So it's got to be in between 3 and 4. So we can make kind of a guess. Again, we can look and say, well, 1160 is quite a bit closer to 1,000 than it is to 10,000. So probably it's closer to 3 than 4. So who knows? Guess 3.2, 3.1 or something like that. If you go to your calculator, you're going to find that it's approximately 3.1. All right, let's try these last two here. Log of 4.2. So again, the idea, pin it between two numbers. This is less than our next power of 10 up is 10. So it's less than 10, right? So it's got to be less than 1. Log of 4.2 has got to be less than 1. And our next power of 10 below that, this way, is actually 1. So it's got to be bigger than log of 1. Log of 1 is 0 if you're going that way, right? Because 1 is 10 to the 0. So if you want to make kind of an estimate of that, we know it has to be between 0 and 1. It's got to be 0 point something. So 0 point, if you're trying to decide what that is, it's you might think, well, 4.2 is closer to 1 than it is to 10, but it doesn't really work in a linear kind of scale like that. You can't say if it's halfway in between, it's going to be halfway in between those numbers. So we might guess, if you're guessing, you might guess 0.4 or 0.5, but you're actually going to find that it's probably more like 0.6. But at least it is helpful to know it's 0 point something, or in other words, that it's definitely between 0 and 1, just for understanding point of view. Now, the very last one here, this number, it's harder to work with numbers that are less than 1 like that, but we can still do the same idea here. This value, if we go down 1 here, it's definitely bigger than logarithm of 0.01. 0.03 something is bigger than 0.01 something. And it's less than the next value up, 0.03, actually it's going to be 0.10. So I know that decimals sometimes can be troubling, but you think 0.3, 0.1's the next one down, and 1.0's the next one up. So we know that the logarithm of this value right here, that is like 1/100th, right? That's like 10 to the negative 2, that value there. So the logarithm of that number is -2. And the logarithm of 0.1 is like 1/10 or 10 to the negative 1. So this is between those two numbers. So we've got log of 0.0315 is between -2 and -1, or it's going to be -1 point something. You again might think about it, well, it's closer to this. You might think it's closer to -1 than -2. You're actually going to find that it's closest to -1.5. But again, it's not so important the actual number that you're predicting there. It's more important to just have an understanding that it's between those two numbers. All right, so that's a bit of an introduction to logarithms, or more specifically, we should say base 10 or common logarithms, because as you move forward, you're going to start to work with logarithms in any base. The concept is going to be exactly the same, and you can extend this same concept to those other bases. But for now, that's common or base 10 logarithms.